10.73, read 10, gas turbine portion of a combined gas steam power plant has a pressure ratio of 16. Okay, so if it's on the combined gas steam power plant, it's a combination between the Brayton and the Rankine. Okay, so we're going to have air going through the Brayton like before. We're going to have water going through the Rankine as before. They do not mix up. Watch out for that common mistake, right? Common misconception. It's two cycles, and they're operating in conjunction, but it's not like the water goes through the Brayton or the air goes through the Rankine. They're completely separated in that sense. Okay, so the 16 pressure ratio, that's for the Brayton, right? That's pressure, the higher pressure over the smaller one. And we think of Brayton, we think two isobaric processes, one heat addition, one heat rejection, and two isentropic processes, one expansion, one compression. We think of Rankine, yeah, the steam power part of it, we think same thing, right? Two isobaric processes, one heat rejection, one heat addition, and two isentropics, a compression and an expansion. Okay, so in terms of the processes, they're exactly the same. Air enters the compressor at 300. So if it's air, we know we're talking about the Brayton at 14 kilograms per second and is heated to 1500 in the combustion chamber. The combustion gases leaving the gas turbine are used to heat the steam to 400 C. Okay, so the rejection of the Brayton is going to be used on the Rankine in 10 megapascals. The combustion gases leaves the heat exchanger at 420 Kelvin. The steam leaving the turbine is condensed at 15 kilopascals. Assuming all the compression and expansion process are isentropic, so we're assuming no reversibilities, right, for now at least. We need to determine mass flow rate of the steam, the power plant output, and the thermal efficiency of the combined cycle. For air, assume constant specific heat at room temperature. So we're using CPs and CVs as a single one. We're doing the approximations, right? So that's why it's very important that you guys understand the difference. Okay, so first thing I want to show you guys, mass flow rate of the steam. We have mass flow rate of air, which is 14. Not to be confused with the mass flow rate of the steam, which we don't know. The net power output, since we have two guys, we have the Brayton and the Rankine, the net power output is just going to be the output of the Brayton plus the output of the Rankine. Okay, and the thermal efficiency of the combined cycle, well, this, like always, going to be the total net output over how much energy we gave to this system in total. Okay, all right, so give me 1 sec. All right, so let's draw this guy. Okay, you're gonna see it's not as bad as it sounds. Draw this guy. So we have temperature on this end, entropy on this end, and I'm gonna first draw the Rankine just like before. Nothing new really. Just state one, compressing it. Simple Rankine cycle, as simple as it can be. Then we heat up, heat up, heat up, heat up, heat up. And we go and drop down all the way here. Okay, so that's our most simple Rankine cycle. And that's why I say you might end up liking this one, because they're mixing up two, they make just a simple. So we go 1, 2, 3, 4, no fancy states, just straight to the point. Right now, the next one we're going to have is the Brayton, and that's going to go on top of it. And I know it's on top because all the energy is going, all the Q in is going to the Brayton, and then the Brayton is giving out energy to the Rankine. So we know this guy, for it to be able to give energy, it needs to be at a higher energy state, right? So my Rankine is going to be, let's see here. So that's going to be start here, and then we have our compression, and then it goes heat addition like so, and then we're going to go make sure I get this right, like that. So for this guy, we're going to have 5, 6, 7, 8. Again, as simple as it can, as the Brayton can be. The only difference on this problem is that we're going to have a state 9 here, which is the exhaust of the Brayton that's giving energy to our system. So let's simplify this. So we have compressor here. We have our heat addition process. So we're going to have, I forgot the name that we give to this guy. It's not the boiler because it's not boiling anything. Combustion chamber. Yeah, combustion. Combustion. We have a turbine here. And then we have the heat exchanger. And this is the biggest difference. And on this other side, we're going to have a pump or the compressor. Same thing in this case, pump. Have a condenser like before. And we have the turbine here. All right, so I'm going to put in blue my Brayton. And I'm going to put in green my Rankine. Okay, so notes, and this is, I want to stress this a lot because of last year. Okay, this is running on water. This is running on air, not on air, but like with air as a working fluid, right? And it's not like on the heat exchanger here inside, air and the water, they mix up, right? It's a heat exchanger. So we have a pipe in which air is going and rejecting heat, and we have a pipe in which water is coming through and giving and absorbing that heat. Okay, so it's different pipes, they're not touching. All right, so from now, we can start solving the cycle. How are we going to do that? I'm going to lay down the information that we have, and we're going to do and we're going to solve the Brayton first, Rankine second. What's information that we have? Well, we have let's separate them again. Let's do Brayton blue, Rankine green. So Brayton, I have the pressure ratio, so I have R of 16, and that's going to be my P6 over my P5. Because it's two isobaric processes, it's also going to be my P7 over my P8. Okay, I also have the temperature, so I have T5 as 300, T7 as 1500. And I have T9 as well, which is the exit for the heat exchanger there, which is 420. What else do we know about this guy? We know the mass flow rate as well. So the mass flow rate of air, which is 14. We know K, right? We're going to use constant K. So we know K is going to be the same always. We know CP, which is not going to change as well. So these are the things that are going to be useful for us. What do we know about the Rankine? The Rankine. What do we know about Rankine? We know temperature T3, which is the one before the turbine, and that's 400 Celsius. We know pressure 2, which is the same as pressure 3. It's the top end pressure, that's 10 megapascals. I also know the lower end pressure, which is 15 kilopascals. Cool, so that's information that we have. As I said, I'm going to solve the Brayton first, have all the properties that we need from Brayton, then I'm going to solve the Rankine, grab all the states for the Rankine, and then finding the things that we need to find is easy, okay? As you can guess, probably beforehand, we're going to do an energy balance inside this heat exchanger here. We're going to do this as a control volume, and because we can't create or destroy any energy, we can use that to our advantage to find the mass flow rate of water. Okay, so let's start with the Brayton. It's probably easy for you guys, we did so many times, so I can find T6 if I have T5. We're relating P6 and P5. And again, I can only use this if it's an isentropic process and if it's constant CPs, right? If it's not, I cannot do this technique. Don't forget that. And then I can also find T8 using exactly the same thing. T7, P8 over P7, K minus 1 over K. It's going to be 1500. 1 over 16. Sorry. Over 16. 2.4, 1.4. 679.3. Okay, so I pretty much defined the whole Brayton already, as easy as that, because we don't have to take into account any irreversibilities or anything like that. It's just, that's pretty much it, right? We can go ahead and calculate how much energy is going into the system, which is especially important in this guy because we only going in the Brayton cycle. And that's going to be when we go from 6 to 7, right? So we can do, again, just because CP is constant, we can do this T7 minus T6. We have all the information, so we can just do that math. That's going to be 141.7 kilojoules per kilogram. Okay, and again, I'm going to repeat what I just said. This guy is especially important because all the Q going into this combined cycle is being given to the Brayton, right? There's nothing on the ranking side of it. So this is especially important. And what we can do now is we can calculate can define the ranking. Okay, so the ranking is going to be very similar to what we've been doing lately, but it's a bit more work. We do state 1. You have saturated liquid and the pressure of, what is it, 15? Five. $225.94. 001, 1014. That's state 1. You can go ahead and find state 2 just by relating the specific volume 1 and the difference in pressure. We went from 10 kilopascals, that's 10 to the 4th, minus 15 kilopascals. All right, yep, that's it. So this guy here is 236. So we got state 1, got state 2. State 3 has been defined from the start because we have both temperature and pressure. So we have, for this guy, we have, what is it, 300 and 10 megapascals. So and just like before, it's the same entropy, right? Isentropic process from 3 to 4. So of course, state, we're going to have to do all that dance again. dance that we always do. We're going to have S4 equals S3, and also know this is 15 kilopascals. We'll see this is a saturated mixture. And from there, we can calculate our entropy. Sorry, our quality. Quality is 75.28%. And I'm rushing through this because we don't have much time. And you know how to do this already. With the quality, we can calculate our entropy, which is 2011.8. Okay, so now we defined the whole ranking. The whole ranking system. Okay, now what I need to do is I need to see how much energy is released from both of these so I can do my energy balance on the heat exchanger. All right, so let's start with, since we're here already, let's go ahead and do the ranking first. So I know the energy output from this guy is going to be the difference between these two guys here. That's going to be the work that the compressor needs. And the work that the turbine releases is the difference between these two guys here, right? That's the turbine. We can do work at the turbine will be H3 minus H4, which turns out to be 1,085.2. And the work on the compressor, now that's only one, it makes our life so much easier. It's going to be just H2 minus H1. And that is just 10.12. Okay, so therefore the work net of this, of the work of the ranking, okay, for the ranking is going to be 10.75. So let's do the same thing, find the turbine and the compressor one for the Brayton. Okay, so the one, let's do work of the compressor on the Brayton. That'll be H6 minus H5. And then on this guy, we didn't calculate H's, right? But we don't have to because we know this is going to be CP delta T, so it's going to be just T, whatever is greater, T6 minus T5. Okay, so the compressor is 364.3. And we can do the same thing for the turbine. H7 minus H8. It's just CP. T7 minus T8. $824.8. So the work of the Brayton is going to be simply how much turbine is outputting minus how much the compressor is taking up, right? It's just the difference between those two guys there. And that is 460. So turbine minus compressor. The work output of the Brayton is 460.5. Make sure I have a separation here so we don't get confused on what we're doing. Okay, let's take one more step back. We just found out, remember we have two systems. Let's go back to our TS. Yeah, there you go. We have two systems. Okay, we have a Rankine and a Brayton. We found out that this guy here has 1,075 output kilojoules per kilogram. And we found out that this guy here has 460.5 kilojoules per kilogram. Now, just by looking at these numbers, you might think, well, that means that my Rankine is outputting more than my Brayton. Not quite true, right? Because we need to take into account what is the mass flow rate through them. And you notice that the mass flow rate on the Brayton is going to be way greater. Right? It wouldn't make sense for the one that has more energy to output less work. You just see that this is going to check out just now. So what do we know about this heat exchanger? Let's look at this heat exchanger here. We know that we have Q out from the Brayton going there, and we know that this is giving away Q in for the Rankine, right? So because we can't create or destroy energy, we can do a little energy balance inside this heat exchanger, and then we can see that whatever energy is being given out by the Brayton needs to be what the Rankine is absorbing. Okay, so we can do that. What would that be mathematically? Well, at the heat exchanger, mass flow rate of air times the output of the Brayton has to be equal to mass flow heat of water and the output of the Rankine. And we have all the information that we need for this, right? Water, H2O. Okay, so in other words, my mass of H2O, which is what we're after, has to be equal to the mass of air that we know times the work output of the Brayton that we don't know, but we can find out easily. I'll probably sub that in. Sorry, let me reverse this. Let me do Q here, Q here. Make more sense. Q out for this guy and Q in for this guy. Now the Q in we know Q out and Q in. Okay, the Q in for the Rankine we know that's just going to be, it's easy for us to calculate, right? It's just going to be enthalpy of 3 minus enthalpy of 2. For the Brayton, it's going to be from 8 to 9. And that's another other thing that students usually forget, because they're used to doing from 8 all the way down to 5, but that's not where the heat exchanger lies, because the exhaust system, if you guys recall what's being said on the question, it's saying that, where is it? The combustion gases leaves the heat exchanger at 420, right? So that means that 420, which is our 9, is what we need to take into account. So that's another trick that may get you. So 14 kilograms that we know times CP times T8 minus T9 divided by H3 minus H2 needs to give us our mass flow rate. We have all these data, right? I have all this information here. And this turns out to be 1.275 kilograms per second. Okay, so the amount of water that goes through, and this is part A, right? This is what part A is asking of us. So the amount of water that goes through this Rankine cycle is 1.275 under the conditions described, right? Under the conditions of the Rankine cycle, the Brayton cycle, and the amount of energy it's going through. And once we know that, then part A and B are quite easy, because we want the output of Brayton, the output of Rankine. That's just grabbing the information that we have and multiplying by the mass flow rate. And if you want the thermal efficiency, we just need to work and divide by what's going in. Okay, so let's recap back to this guy here. Okay, so we have two outputs. We have two outputs, 460 of the Brayton that I'm going to multiply by 14, and 175 that I need to multiply by 1.275. Okay, so if I want the output, the net output, and that's going to be just the combination of Brayton and the Rankine, I just need to multiply by the mass flow rate of each. Okay, so let's finish this off. Where we're going to finish this, probably beneath, so whoever's copying can still copy. Okay, so B the output of the net output of the combined cycle, combined, will be, and we want the power, right? Because the answer is given in power, so we want the power. So it's going to be the power output of the Brayton plus the power output of the Rankine, which in turn is just 460.5 times 14 plus 1,075 times 1.275. And that's going to give us, that's kilograms per second times kilojoules per kilogram, that's kilowatts. This gave me approximately 17.6 kilo. No, I'm the limit of the page. No, I'm not, just kidding. Kilowatts. Okay, and then C, and this is maybe the last tricky bit that may get you. We know that efficiency is just how much output it gets to how much energy is going in, right? So if the power that we get out of this guy is 17.6, what is the amount of energy going in? What's the heat that's going in? What's the number that I need to divide there by? Come again? Just be louder, please.
841.7.
Almost, right? Because this is in kilowatts.
Yeah.
I put 841.7, that's going to be in kilojoules per kilogram. So something else, right? Times what?
1,000.
No. How do I transform my kilojoules per kilogram into kilowatts?
Into mass flow rate.
That mass flow rate, perfect. Which mass flow rate is that going to be?
I don't know. This 1.275 might be. No.
What do you guys think? That's what might get you in this sort of
Would
problem.
we both add it together?
No, guys, no. It has to be 14. It has to be 14 because Q is going in only on the Brayton cycle. Remember? Q is not going in on the Rankine. The Q in of the Rankine is just the Q out of the Brayton. So all the energy is being given to my Brayton cycle. So if I want to know what's the Q in, I need to get the difference from H7 to H6. I need to multiply that by the mass of the Brayton, not the mass of the water, or not the mass of the combination. Okay, so this is going to give me kilojoules per kilogram times kilograms per second. And now we have, on both sides, we have kilowatts here and kilowatts here. So now we can divide and we can get an efficiency that is dimensionless. This turns out to be approximately 66.34%. Okay,